We live?
I think we're live.
I think we're live. We must be.
Great.
Hey, what's up, everybody? I'd like to welcome you to the Audio Programmer Meetup. Sorry for the technical difficulties there. Zoom had moved where the live streaming is, and but we're back. We're here and we're live. And I'm here with Jelle Bakker from the Netherlands. How's it going, Jelle?
Good. Yeah. Thanks for having me.
Yeah, thanks so much for coming. And I'm really excited today because we're taking a journey back into the land of C++ today. And I'm really excited. I'm always excited for C++ and ready to level up my own skill set. So this is a little bit of a selfish one for me. Uh, but just for anybody who might be joining and that's never been here before, this is a meetup that we do every month for anybody who's interested in audio software development and how to create their own audio apps. And one of the most common languages that's used for creating audio plugins and audio apps is C++. And we have Jelle here, who is also known as the CPP doctor, C++ doctor. So he's a very experienced C++ developer who will be talking about lambdas today. Before we start, just wanted to tell you about our audio programmer community on Discord. It's a great place if you're getting into audio software development to get to learn and to get to know other people who are also creating their own apps and plugins. And you can join us there on the audioprogrammer.com/community. I also want to give a big shout out and a big thank you to our sponsors, Focusrite, JetBrains, Juice, and the Audio Developer Conference for sponsoring this meetup. Without them, this wouldn't be possible. And so today, Jelle is going to be presenting a talk called Everything You Need to Know About C++ Lambdas in just 30 minutes. And Jelle's bio says, after years as an independent audio developer working with C++ and Juice, Jelle founded C++ Doctor in 2025, and through his platform, he helps others grow with their modern C++ skills via social media content, mentorship, and consultancy. So if you're looking to get some mentorship for learning C++, Jelle is the person to talk to. And the name of this talk is called Everything You Need to Know About C++ Lambdas in just 30 minutes. Super excited for this talk, Jelle. Go ahead and over to you.
Thanks, Josh. Let's see. Is all good? Can you see the
Yep, all
screen?
good.
Great. Yeah, thanks, Josh. It's really an honor to be here today. And I'm going to try to cover as much as I can in 30 minutes. So you've just introduced me, but I'll just go ahead and just share a bit more about me. I'm an independent audio developer, so I've created Juice plugins, audio plugins, and desktop applications for around the last 8 years now. But this year I decided to shift direction a little bit, also a bit more into the C++ in general, in something that's called C++ Doctor. So I found that this year, and with that I'm doing content mentorship and consultancy. So I'm sharing content on LinkedIn, YouTube, and also have a newsletter that you can subscribe to this QR code if you like. Besides that, I'm busy being currently father of 2 little girls. I try to find time playing cello, and as most developers, drink a lot of coffee. So, all right, yeah, so today, everything Lambdas in 30 minutes. It's going to be based on my ebook that I released this year, I think around 2 months ago, called The Anatomy of C++ Lambdas. So yeah, consider this talk like a short version of that book with the basics of lambdas so that you can really use it effectively in your code. So we're going to start with just talking about what's a lambda, why we need lambdas in the first place, then go more into the theory, and I'll conclude with some practical tips, especially for you Juice and audio developers, how you can make your code more concise and expressive. So if you've been using Juice or modern C++, there's almost no way around lambdas. You've probably seen them in many different ways. For instance, if you've been using Juice slider or Juice components, you can attach callbacks to various things, like you can observe when a slider value changes with the lambda. Lambdas are used in for instance, parameter string conversion. So you can have a custom string for your parameters. They can be used in pop-up menus to trigger events when you click something in the menu. And you can also, for instance, use lambdas to customize algorithms, like customizing how a sorting algorithm works. So they're really everywhere. So it's really key to understand how they work so you can use them effectively. To understand why we need lambdas, let's take a look at code that we could write before we had lambdas, so before C++11. If you wanted to pass a function into another function, like customizing for instance here, a count algorithm, you could do that in two ways, basically. You could either pass a function object or a function pointer. So on the left side here, we have an example where we have a vector of ages, and we want to count how many ages are above 18. And with this object here is above age that constructs with a threshold, and so you can have your own version of is above age, and then since it overloads this function call operator here, it becomes a function object. And that's how you could pass a function object before C++11. You can also pass a function pointer like this. And those were basically the two ways you could sort of customize functions and inject functions into functions. But you can understand there's quite a lot of code, especially this one here, quite a lot of code needed to get the simple thing possible. Just a simple int comparison, you have to write this whole struct. And that's where the need of lambdas came in. So lambdas, they didn't came in to make a sort of new technology or something that wasn't possible. It just makes this possible with a different way of writing. So this struct here we can rewrite with a lambda using just this. So this here is a lambda that's doing the same thing. It takes a threshold by capturing it and copying it into the lambda. And then we write a little function here that takes an age and compresses it. And it's the same thing, but just written much more concise and much more expressive. So what is a lambda? If we go to cppreference.com and search for the definition of a lambda is defined with an unnamed function object capable of capturing variables in scope. So let's break this down a little bit. Let's start with what's a function object. So a function object in C++ is any object that you can treat as if it's a function, so you can invoke it. And that happens through a function call operator overload. So here's a simple example. We have an adder struct that has a simple function operator overload that just sums two values. And you can instantiate it, and then you can invoke it like this. A lambda can be written, we can write the same thing with a lambda like this. So you can see it's very similar, just a little bit different. And the key difference is that the struct adder over here, we have to define a struct. We have to give the struct a name, and you can instantiate it explicitly like this. But a lambda, there is no name. And that's the next thing that I want to touch on. That is a lambda is unnamed. Some call it anonymous. So the object, the lambda object, has no type that we as developer write. The compiler generates a unique type, probably with some kind of name under the hood, but we as developers cannot reference it. So if we want to assign this lambda to a variable, we cannot give it a type. All we can do is just say auto, let the compiler fill in the type that the compiler already knows. Because it's unnamed, we can write very small code. We don't have to worry about coming up with a name for it. The compiler will just do it, and we can just write the lambda without any name, basically. And the last bit of the definition that I want to touch on is capturing, because the capturing capability of lambdas is what makes it really powerful, because you can very easily construct a lambda with captures. So here we are copying x into the lambda, and we don't have to write a constructor, we don't have to write member variables. It's all just implicitly generated for us. So this lambda probably has some kind of constructor that the compiler generates. We just don't see it. It's just very easy to use lambdas this way. But captures are also really tricky. So let's talk a bit more about captures. So yeah, again, the captures are what you write between the square brackets. And the square brackets are the first part of the lambda. When the compiler sees the square brackets, it knows there is a lambda. And you can have no captures, you can have a single capture, or you can list multiple variables with a comma separated in the capture list. And there are different ways of capturing. As you can see, we have, for instance, an X, and then we have %y. So I'll touch on how the different captures work a bit later, but just know there is different way of capturing. You can also initialize new variables with captures. You could say x equals 0, just initializes a new integer in the lambda. So yeah, as I said, lambdas can be really tricky, especially when you are going to use something called capture all or capture all with reference, because this allows you to access anything from outside the lambda within the lambda. And that can become really tricky with asynchronous code, where you do not have the guarantee that the thing you're accessing in the lambda still lives outside of the lambda. So I'll have an example of that also later. So let's look at the first capture example. We have two integers here, x and y, and we capture both in the lambda, and then we just print them. You can see this difference here. We have x and %y. The difference here is that x is copied into the lambda and y is referenced within the lambda. So we capture y by reference, that's how it's called. And because we capture y by reference, modifications made to y after initializing the lambda are seen within the lambda. But since x is copied, we only see the original x. So that's why this prints x1 and y4. I want to show a second example of how captures can be used. And in this example, we initialize a new variable within the lambda. This is not used so much in practice, at least not in code that I see, but can be really useful. For instance, here we are creating a lambda with a count starting at 0. And each time the lambda is called, we're returning a new value and then incrementing count as well. So you can use this in combination with to generate to fill a vector with incremental numbers 0, 1, 2, 3, 4. You might notice this mutable keyword here. A mutable is what's needed when you want to modify the capture within the lambda, because lambdas by default, they capture everything as const. Unlike other things in C++ that are all mutable by default, things in lambdas are by default const. So if you want to modify them, you have to add the keyword mutable. I want to again point out that a lambda is just a function object, and it's just a different way of writing the same thing. So this count here, we can write that in a different way using this struct here. So you could have a struct counter with an int count member and then a function call operator. It's doing the same thing, and then you can instantiate it over here and pass it. It's just much more concise doing it this way. So as I said, there are different capture types, and I've listed some of these here. By the way, this comes from a free Lambda cheat sheet that I made. You can download that for free with this QR code if you like. I'll go over each capture type one by one. So the first few I already touched on. The first one, if you just mention a variable name in the Lambda list, it's going to be captured by value or copy. If you prefix that with an ampersand, you capture it by reference. And you can also do an init capture by assigning it to a value like this. There are a few more special capture types. If you specify the equal symbol of the equals symbol, it means capture everything that's used in a lambda by copy. And similar, there's the reference symbol, which means capture everything that I use by reference. And this one, as I said, is really tricky. There's also finally the this, which means capture things from the current object that we're in. So yeah, the ampersand capture is really tricky. So let's consider this example here. Let's say we have some menu bar with an about button. When you click that, we want to show a dialog showing the plugin name or something. And we give a plugin name as part of the constructor of menu bar. And we're saying, let's capture everything by reference and then print the plugin name. So you might already guess, the problem here is the lifetime of plugin name is not the same as the lifetime of the lambda, because the lambda is going to be executed sometime later when I click the button, but plugin name is probably already be destroyed, and this can cause a crash. And this can be really tricky because it's so easy to just write the code like this, and the compiler will just compile it for you, maybe not even show a warning or anything. But what you have to do is you have to copy it into the lambda. And if you've been using lambdas a lot, you've probably been through some kind of bugs or crashes like this. And once you start using lambdas a lot, you will become familiar with these problems. But in general, I would recommend avoid this type of capture if you can, or be really careful with it. Another lifetime example, also a Jews example. Let's consider a different example where you have a component and you want to do a version update check. It's a really common thing to do in products to notify the user of a new version that's available. And usually what you'll do is you'll spawn a thread, perform a network call to the server where you check the version, wait for the result, and then when the result is received and you see there's a new version, you will want to notify the user, do something on the user interface showing a dialog of some kind. And again, here's the problem of lifetime, because we're spawning the thread, and then you can use the Juice message manager call async to go from the background thread to the main thread where you can do UI operations. But we're doing a repaint of main component here, but how do you know that main component still exists? That's the big question here. And the thing here is again subtle, because this might just be fine. This might run fine in most cases, because in most cases, the result of the network call is going to arrive pretty soon. And this main component will probably still be around when you want to do a repaint and show dialog. Luckily, Juice has a solution for us. Juice has a safe pointer, which is similar to weak pointer, if you're familiar with two shared pointers. It essentially gives you access to the component and get to know if the component has been destroyed. So you can do a check over here, if not safe pointer, and this will return if the main component has been destroyed. So you can only do the repaint if the safe pointer, if the object is still around. So this is a fine way of doing it. I want to show an even better way of doing this with Juice, because Juice has a way of doing this without lambdas at all. We can use overrides of Juice thread and Juice async updater to do all this work within overrides. And by doing it this way, you have to guarantee that all these functions run within the lifetime of the object, because that's how Juice handles these things. So you have a start thread that starts the thread, and the run does the run function runs on that thread, and then you can do a trigger async update to trigger an event to happen on the main thread sometime later. And Juice will, in between, always make sure that if the object gets destroyed, everything just aborts. Okay, time for a little puzzle about captures. So I've mentioned that captures are basically the members in your lambda objects. Like we've seen the counter example, where count in a lambda is sort of the same thing as having a count member in a struct. So when you see captures in a lambda, you should think about them as being members within the object. So saying all of that, let's consider what sizes these lambdas are, considering they're just objects. So we have 5 examples here, 2 where we capture explicitly, and then 3 where we capture with the equal sign, which again means capture everything by value. And the compiler will then look at the body of these and only capture what's being used. So I'll just pause for a moment, and then you can take a look and see if you can answer these questions. All right. Here are the answers, so I'll walk you through them. So the first 2, I hope, are obvious. We explicitly state what we want to capture, and here we captured just one X. So the size of this lambda is going to be the size of one member, it's just 1. This one we have 3, so the size is going to be 3. For 3 and 4, what happens is the compiler will look at the body. It will see here that we're just using X. So the compiler will essentially just put X here. For this one, same thing, except we're using X, Y, and Z. So the compiler will just put X, Y, Z in here. So that's why this is 1, this is 3. The last one is a bit more tricky, and since we're not using anything, you might think that the size is just 0, but in C++, objects cannot have a size of 0. So that's why this one has a size of 1 as well. Let's talk more about syntax of lambdas. So one interesting thing is you can use auto as parameters, which when you use auto, the lambda becomes a so-called generic lambda, basically becoming a template function call operator overload. So you can now, in this example, you could call sum with anything that can be summed, basically. It could be floats, integers, different objects that can be summed. And then the compiler will just generate for you different function call operator overloads within the lambda. This is, by the way, not unique to lambdas. You can these days, I'm not sure since which C++ version, but you can now write auto also for normal C++ functions and also for return types of C++ functions. About the return type, it's also interesting because lambdas by default, if the compiler can deduce the type that you're trying to return. So if the compiler can see, oh, you're returning an int, then you don't have to do anything, basically. The compiler can just use the int as the return type. But sometimes it's not trivial. Like for instance here, we have different return types. We have here an integer, then a float. And the compiler cannot deduce the return type. The compiler does not know what you want to return. So the compiler will throw a compiler error. We can fix this by adding a so-called trailing at the end, which is the return type of the lambda. And this will now return a float for both, and the compiler will perform an implicit conversion from this int to a float. However, I do want to advise not using this if you can. I would recommend making sure that return types you put in match, so you don't get implicit conversions that you don't want. But the return type can also be useful in another example. So let's consider this example where we have a create shape lambda that creates a shape, and we have different shapes. We have a circle, triangle, probably other shapes that all inherit from a base class shape. And our intention is we just want to get a base class shape back. We don't care if it's a circle or triangle. But the compiler does not know that's our intention. The compiler just sees a circle and then a triangle. And the compiler, even though it knows they have a common base class, cannot make the decision for us that that's our intention. So the way to fix this is by adding the trailing, the return type. We say we want to get a base class shape back, and then the compiler will just convert for us the circle to a base class pointer. There are a few specifiers you can add to a lambda. I already touched on mutable, which makes the captures non-const. There are a few more. There's const expr, const eval, and static, and those all, they behave the same as they do for normal functions. Const expr though, if you don't specify it and the compiler knows the lambda is const expr, you don't have to add it. The compiler will add it implicitly for you. And there are also in lambdas something called attributes, so you can have different attributes, but that's beyond the talk of today. And I want to finally quickly mention an interesting feature since C++ 23 called explicit object parameter. And this is a feature that goes beyond lambdas, but we can use it in lambdas to get recursion possible. What it is, you get a pointer to the current object as the first argument by inserting this syntax here. And before we had this feature, recursion with lambdas was quite difficult. It wasn't trivial. But now that we have this, you can call the lambda from within the lambda, making things like a factorial possible. How do we pass lambdas around? You have basically two ways how you can pass a lambda. The first way is with std function. So this is probably the most common way in many people code because it's really flexible. So imagine you have a button and you want to inject into the button constructor a function that's called when a function needs to draw itself. So you can decouple how a button is drawn from the button itself. So you you could use a std function for that, and then you can insert a lambda like this. So std function accomplishes all of this through something called type erasure, which means the std function signature doesn't show you what's expected as a function. You can put in a function pointer, a function object, a lambda with captures, without captures. All of this is really flexible, and that's all done through type erasure, and that's really interesting to read about. But the key thing to take away is that it uses the heap to accomplish this, and polymorphism, and there's a cost to all of this. There's a performance cost and a memory cost. And so std function is not the most performant thing, but it's really flexible because you can easily pass functions around also throughout different translation units, and you don't need things like templates or anything. Because the second way of doing it is with templates. Because again, a lambda is a function object. If you think about it that way, you could just pass it as the object directly. The only problem is we don't know the type of the lambda because we never specified the type, because the compiler generates for us the type. But since the compiler knows the type, we can use that in the context of templates. So, for instance, here we have a call function that calls a function that you pass it in. And the type of the function it expects is a template, and then the compiler can replace this type with whatever type the lambda is. This technique is used a lot in code where the lambda is needed for a more shorter amount of time, like in algorithms, for instance. All these std algorithms in the C++ std library, they often have an argument where you can put in a custom function or lambda, and this is all done through templates. So those are the two ways. The first is really flexible, easy to use, and is used when you need to store a lambda for a more long time, like in a GUI component, or pass it throughout translation units. And the second one is more used in shorter time functions. I want to talk about a few myths that are around about lambdas. The first one that I hear a lot, and even I read this online when I Google what's a lambda, you'll read it's a little function. And just want to point out again that a lambda is a function object, and it's really different from a function, because a function cannot have members, cannot have any storage or state. And it's just key for understanding what a lambda is to know it's a function object. Second myth I also hear is that people mix up lambda with std function. So as I just explained, std function, it can wrap a lambda, but it can also wrap a function object or a function pointer. And it's just something that wraps an invocable object. But a lambda is just a function object, like any object. And if you just declare a lambda, it doesn't have the same properties as std function, like the overhead or the heap allocation. A lambda is not slow. That's the third myth. People think that because of this weird syntax and captures, and that there's some overhead in performance, but lambdas are not slow. You can definitely use them even in like real-time audio codes. The compiler can see your entire lambda and is able to perform a lot of optimizations. But again, yes, if you store a lambda in a std function, there will be a performance impact, although always measure. I want to conclude with some lambda tricks, how you can use lambdas in your code. The first one, I use this a lot to make my code more concise, is something I call little helpers. You might have written code like this, where there's a lot of repetition. You have like a button that you want to configure, and you do that multiple times. And you might have considered putting this in a separate member function, but then the problem with that is you now have a new member function in your class that you only really use during the initialization and the construction phase of your component. So what I prefer is just putting a lambda in, just to reduce the repetition, just a little helper lambda within the context of your constructor that you don't expose to the rest of your class. Second little trick is something called immediately invoked function expressions, which is a lambda that you, after defining, you invoke it immediately. And that can be a solution for when you have a lazy initialization happening, which is shown over here. So for instance, you sometimes have some variable that you first construct, and then based on some conditions, you assign the value. But conceptually, it's not non-const, it's const, you just delay the initialization. So if you could, you would like to make it const, really. And the way to do that is you could put the string logic inside the little lambda and then invoke that right away after defining it. Now you can make this a const. It's just a result of this lambda. And again, there's no performance impact here. The compiler can just optimize this for you. Trick number 3, lambdas can be converted to C pointers if you're interacting with C APIs, or you have a function that takes a function pointer. You can convert the lambda to a C pointer if the lambda does not have captures. That's the only condition. Because if the lambda has captures, you can imagine there is state and there is storage in the lambda. How do we get that in the function pointer? Well, you can't. So if a lambda has no captures like this, you can convert it with this plus symbol over here to a C pointer. Lambda 4 is another little helper. In Juice, you might have written code like this, where you need to lay out all your components. This example here, I have repetition again. I have rows with a label and a button next to each other, and I want to just lay them out one by one. And instead of adding a new member function to the class to help us reduce repetition, I just add a little place row lambda that just does the work for us. And it's much more readable, much more easy to use. Trick 5, lambda nesting. Lambda can really open the world to what's called functional programming, where you have functions generating other functions, all those kind of things. So for instance, you could have a lambda called make multiplier, takes a factor and returns to you a new lambda that takes a number and multiplies that by that factor. So when you call this make multiplier 3 and you call that with 10, you get 30. You can also do a similar thing with functions. So you could have a lambda combine taking two functions, lambdas in this case, and returns to you a new lambda that calls one function with the result of the other function, essentially. So there's all these interesting things possible. And the last little trick that will be the conclusion of this presentation is this I came across recently, is within the context of Juice Abstract FIFO. So let's say you have an audio thread with incoming audio and you want to display that on the GUI. Usually you'll have some kind of communication. You will write the samples to a buffer and read those buffer in the GUI thread. And you can use Abstract FIFO to help you with that reading and writing. So let's say we have a process block with the buffer, and we want to write each sample we want to write to this buffer. We can call FIFO write, giving the number of samples you want to write, and then you get an object back. I think it's called scoped write or something, that has a function called for each that takes a lambda that it will call for each of those samples, expecting you to perform the write within that lambda for each of those samples. It will give you the index where to write in the buffer. All you have to do is just increment some counter in the buffer, making sure that you write the next sample of the incoming buffer each time. And we can define a counter like sample index over here and just increment that each time the lambda is called. And once you become familiar with lambdas, you'll start to use them everywhere. And we can even make this more concise by not having sample index over here, but just define it over here. And now we have a FIFO write function, just so concise like this. So yeah, thank you for watching. If you want to follow me, I have a few links here and a discount code for the audio programming community for my ebook. And I hope you've enjoyed this presentation.
Thank you so much, Jelle. That's awesome. And if you can send me the link to the book afterwards, I'll make sure that we put that on the Discord for you as well.
Thanks. Yeah, that's awesome.
Yeah, really cool, really cool. Let me see if we have any questions. So far, we don't. But Rerd Adema, fellow uh, developer from the Netherlands, says hi. So
Nice watching.
question. Great. I'm going to put the link in the chat as well. Can you send me the link to the book on LinkedIn?
Yeah, let me. I'll just keep this open. This. I'll send you a link.
Okay.
Do you have any questions, Josh?
Many, but I'll probably just need to walk through the video again
Yeah.
just to make sure that I'm actually digesting everything properly.
Yeah, it
Many
was a lot.
questions, but I'm too embarrassed to ask them here. Yeah. No, great presentation. And like I said, it's one of those that I'll probably need to um, check out again myself, just to get just to digest everything. But I think it was fantastic. We have a question from David Dobreen. Hey, David, good to see you here.
Nice.
Who asks, do lambdas have a performance penalty on the audio thread compared to member functions?
Good question. So my answer would be measure. That would be my first answer. But second, I would say there is no performance cost. I've seen some code examples where the Lambda code was written and the compiler just completely optimized away the Lambda. So it might even be, I'm not sure like what compilers all can do, but it might even be even better than a member function, especially if the member function is virtual or the compiler cannot inline the member function, then a Lambda is even better than a member function.
I'm going to be buying your book as well here. So let's see. Does anybody else have any questions? While we're waiting for other questions, once again, big shout out to our sponsors, Focusrite, JetBrains, Juice, and the Audio Developer Conference. If you haven't registered for the online event for the Audio Developer Conference, be sure to do that at audio.dev. That'll be a fantastic event. That's online. It's free as well. So hope to see you there. We'll be there as well. Doesn't seem like we have any more. Oh, here we go. We have a question from Yes Tur, who asks, can you talk a little bit more about the difference between captures, such
Mhm.
as capturing by value, capturing by pointer, capturing um,
Yep.
by reference?
Let me open the slides. Yeah, all right. So let me think what I can say more about this. I'll see if I have a better example. Let me think for a moment. It's just key to understand what the differences are. And the best way to learn this is to start not using the capture all, because you'll see when you use this in practice that at least I see myself doing this. I just use capture all by reference a lot because it's like the most convenient one. It will just allow you to access everything from outside, and you don't explicitly state what you are capturing. A better way to start is just capturing nothing and just add the things you want to capture. And there's also this myth that capture by value is slower than capturing by reference. And that's also not necessarily true. It depends, of course, on the object sizes. But again, the compiler is able to also perform optimizations if it can see your intention. But again, yeah, these are the capture types that are around. I'm thinking if there's more I can say about that. Yeah, sometimes the init capture can be used to not just do something like x equals 0. I'll open some code. Let me see.
While you're doing that, is the difference between capturing by reference and capturing from object that capturing by reference has only access to members that are within the scope of the function, and captured by this gives you access to all class
Yeah.
members?
So yeah, so the okay, so can you see this code? Is this clear? So
Yeah,
I can
I'm
write.
still seeing the capture
Oh,
types.
sorry. Uh, anyway, okay, doesn't matter. So okay, so the most broad one is capture all by reference. That just gives you access basically to the same things you have access to outside of the lambda. It's like the most broad one. Then you have this. This gives you access to the current object, like the current members. I want to like show my screen. Let me see if I can do that. Can I like stop sharing? Well,
I could force it.
it's okay. Oh, I can see it here. Okay, I'm sharing my Xcode now, hopefully.
Right. Live coding. I'm excited now.
Yeah. Let's see how this goes. So let's say you have like my struct and you have an int, you have a int here. Let's also have an int here. And so this one, with this one, you have access to everything, right? You can say print x, y, and z by reference. So if you change, let's say if you change this is a lambda, let's assign it, and then you modify something over here, and then you call it, it will see all these modifications. That's like, let's put here y, just makes more sense. Okay, so if we call this, let's put in a comma. Okay, so we get 1, 2, 3. Great. Now, if we modify something, like let's say we make x 5, let's print it twice. We print it here, we modify x, we print it again. Yeah, so first you see it's 1, 2, 3, we change something and it sees the change, right? It prints 5. So it sees the change you just made. If you do this, lambda. That's an interesting warning, actually. Never seen this warning. This actually captures z. Implicit capture of this with a capture default of equal sign is deprecated. Okay, somehow you could in the past capture member functions through the equal sign, but that's now deprecated. So actually this is sort of deprecated. But anyway, you can see we get a copy. So we modify something, but it's not seen in the lambda because this is copied into the lambda. Let's do this. So now we have access to the member functions of my struct. So you can see the error. We do not have access to x because it's not a member function, not a member variable. We do not have access to y either because it's also not a member variable. We only have access to z. So that's what this does. You get access to the members. So
Yeah.
it's a bit more strict than it's not like so this one you have access to X, Y, and Z by reference, and this one you have access to Z by reference. It's important to mention. These don't compile, so we can just print Z. And oh, let's modify Z. Let's make Z. Let's do it like this. Okay, so Z is now 7, and it will see this the 7 because it's this captures by reference, but only the member variables.
Right.
Um, mm, 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 mm. Yeah, there's explicit capture, so you can say just want to capture Z by copy. Yeah, so this, okay, so if you want to capture a member variable, you actually cannot do it this way. You have to sort of, well, I must say I'm still struggling to understand this, but yeah, if you want to capture a member variable inside a lambda, you cannot do it this way because this only applies to local variables within the function you're in. You can reinitialize it like this. This is shadow. Let's make this a different name. C underscore. Okay, so if you want to capture a class member by value, so by copy, you cannot do that with just C. This don't compile. You have to use init capture, so you give it a new name and then you assign it over here. Somehow this worked, but this was deprecated. We just signed a warning. Okay, what else can you do with captures? Yeah, so you can like list multiple captures. You could do X, Y. This is the best way. You're really intentional here. You're saying what you want to capture instead of doing like this. You just have no. This is the most tricky one because of that string example I just showed. And that's really common problem with lambdas is you do this and then you access data and sometimes you even have like it's not so uncommon. You do some stuff and then you create a second lambda or something, and you just lose sight of where things are. If you did do this again, this now can access everything from everywhere, and it's just really can get really nested and complicated easily.
Mm-hmm.
Okay, I hope that's a little bit clear.
Yeah. Yeah. Thanks for that. Um, so, Yester has a follow-up question, and they ask, how do we know when to use these object captures? So, um, star this, um, just this, and ampersand this. But you would only use this without an ampersand or without a star in front of it, right?
Yeah. The star has no real place with captures. You star is just to dereference like that. That's
Right.
like this. This is not a thing. This is not like you cannot or like we have a pointer like this. This is not like you cannot write this in a lambda. Let me clean this up a little bit.
He's
Let me clean this up a little bit. So yeah, okay. So the keyword this is a bit confusing because this is you can also use this in the context of outside of lambdas. You could say like you could do this. You now have a pointer to the instance you're in, and let's say you have like you can access x through this way. It's the same thing as just saying x, but you get a pointer to this. So this has in outside of lambdas, this just means a pointer to my strict. But then in context of a lambda, it's a bit different because you don't get a pointer really. You get a reference because you can access x directly. You don't have to say like this or something.
they were saying as if you were trying to dereference this. So the star
Yeah,
before this.
like
That's not
this.
that's
Yeah,
not a
that's it's not a thing. No, no.
yeah. Well, it is a thing, but not in this context.
Yeah, exactly. It's you have all these keywords that mean different things in different contexts. Even like the square brackets, like it's used for arrays, right? And then now it's used in lambdas. It's just real, and they're totally unrelated. It's don't know who came up with this, but it's a bit confusing.
Um, we have a question from Oliver. Oliver, maybe you might want to check this talk again after we're finished. But um, he asks, "What on earth is the point of lambdas in C++?"
Oh no.
If you could summarize it in one sentence, what would you say, Yella? I would say a small. If I would summarize it, and you could tell me if my understanding is off, I would summarize it by saying um, something like a function, but that you don't need to write a whole, not big enough that you need to write an entire separate function for. Would
Yeah,
that be so like a
exactly.
small function? I'm trying to say it without
So the goal is to write less code, essentially.
yeah.
I would say that like you can you can do everything without lambdas. You don't need to use lambdas. If you don't like them, you no, don't use them. But if you want to write less code, more expressive code, you can use lambdas. Because this here, I'll just show that one more time. This example, I like this example. Maybe I'll make it even better. Um, let's say we have a counter struct that you can invoke because it overloads the function call operator. Returns to you. Let's call this count. And you can also construct it with a default value, with a initial value. So you could say counter starts at whatever, 5. Oh, I need this. Yeah, so this is, okay, so just a syntax thing about function operator overload. This says it's a function call operator overload, and then this is your parameters. So this is no parameters. So you can call this as if it's a function because it's a function object, because it overloads the function call operator. We call this a few times. And it starts from 5 and then prints 5, 6, 7. Okay, so we can write the same thing, much more concise with lambda. You say auto counter equals. So this again, these are your member functions. So I'll just do the same thing. By the way, you don't have to add a type here. You actually cannot add a type. You just say count equals 0, and the compiler will see this as an integer. It's kind of like saying auto. And then return count plus plus. We have to add mutable though, because we're mutating something in the lambda. So yeah, I mean, hope this is convincing. Like this is the same thing. Oh, well, let's start from 5 also to make it, yeah, this is the same. So yeah, destruct, this lambda. I guess the only advantage of this is if you want a reusable counter that you use in multiple places in your project, and okay, sure, you can have this as a sort of reusable object. But if you just need it like in place, just need it somewhere, you can do it just this way. Let's see if this actually prints. Yeah. 5, 6, 7. Yeah, there you go.
I love this live. Feels like the tension rises when live coding comes into the presentation.
It's good, isn't it? Yeah.
So DeWitt from the chat had really a great way of describing it. Lambdas, which is a small anonymous function you can write directly in your code. Yeah.
Yeah. Except, and do want to add one thing, is that is actually function object and not a function, because if it's it can have state, it can have members. So I would say if you add the object word there in between, because there was one myth that I touched upon in the presentation is, and it's, I mean, I want to be correct, and saying it's a function, you miss the point that it has member variables and it's actually an object that has the same properties as object. You can pass it, you can copy it, you can move it.
Great. Okay. I think that's it for questions. If anybody else has questions, be sure to slip them in within the next 30 seconds. In the meantime, thank you so much, Jelle. Once
Cool.
again, for anybody who's looking for mentoring on C++ and best practices, I could probably use a couple of those lessons. Uh, I recommend getting in touch with Jelle. All of his contact information is in the video description below. And nobody has responded to any shout out for questions. So on that note, we're going to wrap up here. So
Cool. Thanks so much, Josh. It was great.
yeah,
Great
thanks so
meeting you.
much. This is really educational. And like I said, what I'll need to do is I need to digest this video again myself and step my game up on lambdas. And yeah, we'll be in touch. Thanks again as always. And we will be seeing everybody next month for the next audio programmer meetup. News about that will be soon. In the meantime, happy coding and see you soon. Take care.
Cool.